Close your eyes for a moment and imagine floating gently in the inky blackness of space, where you can see all the planets are aligned perfectly and the sun is rising slowly. Far away from the hustle and bustle of everyday life, further than any dream you've ever had, tonight we embark on a journey to unravel one of the universe's best-kept secrets, a secret so vast and intricate it dwarfs even our wildest dreams, the cosmic web. This isn't just any story, it's an invitation to explore the very structure of the universe, a network of galaxies and matter stretching billions of light years across space. Think of it as the universe's hidden skeleton that is very huge and still growing. As we drift together through this cosmic landscape, allow the soothing rhythm of my voice to lull you into a state of deep relaxation. Feel the weight of the day melt away as we explore the filaments and voids of space, a journey designed to quiet your mind and prepare you for a restful night. So, as we begin, I'm curious, where are you joining us from tonight, and what time is it where you are? Now, let's journey together into the heart of the cosmic web. Now, let's turn our gaze to the very beginning, an instant often called the Big Bang, 14 billion years ago. In the immediate aftermath of this monumental event, the universe wasn't as structured as it is today. Instead, it was an incredibly hot, dense soup of particles. But even in this seemingly uniform state, there were tiny differences, minuscule fluctuations in density from one place to another. Think of it as if the universe, in its infancy, had a slight case of cosmic acne. These tiny blemishes, these slight over densities, were the seeds of everything we see today. Gravity, the relentless sculptor of the cosmos, began to amplify these small fluctuations. Regions with slightly more mass began to pull in even more matter, gradually growing denser, while the less dense areas gave up their matter, becoming emptier. Over hundreds of millions of years, this process created a vast network of interconnected regions of high density, forming the backbone of the cosmic web. These denser regions eventually collapsed under their own gravity, giving birth to galaxies and clusters of galaxies, lighting up the universe like diamonds scattered across a velvet cloth. In between these dense clusters stretched long, thin filaments of matter, like cosmic bridges, connecting the bustling cities of galaxies. These filaments are the highways along which matter continues to flow, feeding the growth of galaxies and contributing to the ongoing evolution of the cosmic web. It's a process that continues even now, billions of years after the Big Bang, with the cosmic web still growing and evolving, shaped by the relentless pull of gravity and the mysterious influence of dark matter. As we consider that the cosmic web connects all things, next we'll explore the invisible scaffolding that supports this majestic structure, dark matter. Transitioning from the visible to the invisible, we now turn our attention to one of the most mysterious and influential components of the cosmic web, dark matter. Unlike the galaxies and gas clouds we can see with telescopes, dark matter doesn't emit, reflect, or absorb light, making it invisible to our eyes and instruments. Yet, despite its elusive nature, dark matter plays a crucial role in shaping the structure of the universe. Imagine the cosmic web as a vast, intricate sculpture. The galaxies and clusters we see are like the detailed features on the surface, but dark matter is the underlying framework, the hidden scaffolding that holds everything together. Its gravitational influence is the force that initially drew matter together, creating the denser regions that would eventually become galaxies and clusters. In the early universe, dark matter formed a network of gravitational wells, attracting ordinary matter like a magnet attracts iron filings. These wells acted as cosmic seeds, around which galaxies and clusters of galaxies began to coalesce. Without dark matter, the gravity of ordinary matter alone would have been too weak to form these structures in the time available, given the expansion of the universe. Think of it like this: if the universe were a cake, ordinary matter would be the flour and sugar, while dark matter would be the baking pan, giving the cake its shape and structure. Galaxies, drawn together by the gravity of dark matter halos, formed along these filaments, creating the vast network of interconnected structures that define the cosmic web. The presence of dark matter also explains why galaxies rotate faster than they should based on the visible matter alone. The additional gravity provided by dark matter prevents galaxies from flying apart as they spin, acting as an invisible glue that holds them together. This mysterious substance accounts for about 85% of the matter in the universe and is indispensable in the cosmic web's construction and evolution. Now, with an understanding of the critical role dark matter plays, let's explore how galaxies themselves act as cosmic beacons within this vast structure. Considering this intricate dance of gravity and unseen matter, let's now bring the spotlight onto the galaxies themselves, which serve as luminous landmarks within the cosmic web. These sprawling islands of stars, gas, and dust aren't scattered randomly throughout the universe, but rather, they cluster together in specific patterns dictated by the underlying structure of the cosmic web. Imagine each galaxy as a brilliant star on a celestial map, its location precisely determined by the gravitational forces acting upon it. Much like cities connected by roads, galaxies are linked together by filaments of dark matter and gas, forming an immense interconnected network. These filaments act as cosmic highways, guiding the flow of matter and influencing the formation and evolution of galaxies. Within the cosmic web, galaxies tend to congregate in clusters and superclusters, the densest regions of the network. These cosmic metropolises can contain hundreds or even thousands of galaxies, all bound together by gravity. Our own Milky Way galaxy resides in the local group, a relatively small cluster of galaxies that also includes Andromeda and several smaller galaxies. The distribution of galaxies within the cosmic web isn't uniform. Instead, they form a complex pattern of dense clusters, long filaments, and vast, empty voids. This pattern resembles a cosmic foam or sponge, with galaxies tracing out the walls of the bubbles and filaments, forming the edges. By studying the distribution of galaxies, astronomers can map out the underlying structure of the cosmic web and gain insights into its formation and evolution. Each galaxy, with its unique properties and history, contributes to the overall tapestry of the cosmic web. From giant elliptical galaxies to spiral galaxies like our own Milky Way, each plays a role in shaping the structure and dynamics of the universe. Together, these galaxies illuminate the cosmic web, revealing the hidden architecture of the cosmos. Now, shifting our perspective slightly, we will turn our attention to the long, thread-like structures that connect these galaxies, exploring the filaments of the universe. Turning our gaze towards the very sinews that bind the cosmos, we find ourselves amidst the filaments of the universe. These are the grand, thread-like structures that form the backbone of the cosmic web, stretching across billions of light years and connecting galaxies in a vast, interconnected network. Imagine them as immense cosmic rivers, not of water, but of galaxies, gas, and dark matter, flowing through the emptiness of space. These filaments are not merely empty strands. They are dynamic environments where galaxies are born, evolve, and interact with one another. Within these elongated structures, galaxies tend to align themselves along the filament's axis, creating a striking visual pattern. This alignment is a result of the gravitational forces exerted by the filament's dark matter backbone, which draws galaxies inward and channels their motion along its length. These filaments serve as pathways for the flow of matter throughout the universe. Gas and dust are funneled along these cosmic highways, fueling the formation of new stars and galaxies. As galaxies journey along these filaments, they may collide and merge, triggering bursts of star formation and transforming their shapes and properties. The density of galaxies within filaments is much higher than in the surrounding voids, making them favorable environments for galaxy interactions. These interactions can lead to the stripping of gas, the merging of galaxies, and the formation of supermassive black holes at their centers. Astronomers use various techniques to study the filaments of the universe, including mapping the distribution of galaxies and observing the faint glow of gas that permeates these structures. By studying their properties, scientists can gain insights into the nature of dark matter, the formation of galaxies, and the large-scale structure of the cosmos. These filaments, stretching across the vast expanse of space, represent the hidden architecture of the universe, connecting galaxies and shaping the evolution of the cosmos. As we continue our journey through the cosmic web, we now navigate into the seemingly empty spaces that lie between these great filaments to explore the voids between the threads. Now, let's turn our attention to the other side of the cosmic tapestry, to the vast, seemingly empty regions that lie between the glowing filaments. These are the voids of the universe, immense bubbles of space, some spanning hundreds of millions of light years across, that hold a profound significance in the cosmic web. They are far from being truly empty. Rather, they represent regions of extremely low density, where the formation of galaxies is suppressed, and the average density is significantly lower than the rest of the universe. These voids are not static entities. They are dynamic environments that evolve over time. As the universe expands, voids tend to grow larger and more spherical, pushing the surrounding filaments and walls of galaxies further apart. This expansion is driven by dark energy, the mysterious force that is accelerating the expansion of the universe. The formation and evolution of voids are closely linked to the distribution of dark matter. The gravitational influence of dark matter draws matter together, creating the dense filaments and walls of galaxies, while simultaneously emptying the voids of their material. In essence, voids are the negative space of the cosmic web, their existence and properties intricately tied to the distribution of dark matter and the expansion of the universe. Although voids appear empty, they do contain some matter, albeit in extremely low densities. This matter primarily consists of diffuse gas, known as the intergalactic medium, which is left over from the Big Bang. This gas is extremely tenuous and difficult to detect, but plays a crucial role in the cycling of matter throughout the universe. Galaxies that do reside within voids tend to be smaller, less massive, and less evolved compared to galaxies found in denser environments. These void galaxies offer valuable insights into the processes of galaxy formation and evolution in isolation, free from the influence of interactions with other galaxies. Studying the properties of voids allows astronomers to probe the nature of dark energy and the expansion history of the universe. The size, shape, and distribution of voids are sensitive to the properties of dark energy, making them valuable tools for cosmological research. The voids, far from being empty and insignificant, play a crucial role in shaping the large-scale structure of the universe. As we continue our exploration of the cosmic web, we now shift our gaze towards a mysterious entity that exerts a powerful gravitational pull on galaxies across a vast cosmic region, the Great Attractor. Now, let us journey towards one of the most enigmatic puzzles of the cosmos, the Great Attractor. This gravitational anomaly, located approximately 250 million light-years away in the direction of the constellations Centaurus and Hydra, is a region of space exerting a powerful gravitational pull on galaxies, including our own Milky Way, and it is one of the biggest mysteries of the space. Its existence was first inferred in the 1970s, when astronomers noticed that galaxies were deviating from the smooth expansion of the universe, moving towards a common point in space. The scale of the Great Attractor is immense, spanning hundreds of millions of light-years. It lies behind a region of space known as the Zone of Avoidance, an area of the sky obscured by the Milky Way's dusty disk, making it difficult to observe directly. The Great Attractor is not a single object, but is believed to be a concentration of mass, possibly a supercluster of galaxies, pulling everything towards it. Scientists believe that the Great Attractor is likely composed of a massive supercluster of galaxies, a region where thousands of galaxies are clumped together by their mutual gravitational attraction. These superclusters act as cosmic magnets, drawing in surrounding galaxies and influencing their motion. One of the challenges in studying the Great Attractor is its location behind the Zone of Avoidance, which obscures much of the light from distant galaxies. However, astronomers have used various techniques, such as X-ray and infrared observations, to peer through the Zone of Avoidance and map the distribution of galaxies in the region. These observations suggest that the Great Attractor is indeed a massive concentration of mass, consistent with the presence of a large supercluster. The gravitational pull of the Great Attractor affects a vast region of space, influencing the motion of galaxies over hundreds of millions of light-years. Our own local group of galaxies, which includes the Milky Way, is being pulled towards the Great Attractor at a speed of approximately 2 million kilometers per hour. The nature of the Great Attractor remains a topic of ongoing research. While the presence of a massive supercluster is the most likely explanation, some scientists have proposed alternative theories, such as the existence of dark matter structures or even modifications to the laws of gravity. As we continue to explore the Great Attractor, our cosmic voyage takes us to the grandest structures in the universe, the superclusters, where galaxies congregate in vast groups, forming the cities of the cosmos. As our exploration unfolds, consider superclusters, the universe's grandest structures, where galaxies congregate in vast groups. These colossal formations are the largest known structures in the cosmos, stretching across hundreds of millions of light years, and are the last stepping stone before we view the universe on the grandest of scales. They are truly a sight to behold. Imagine them as bustling cosmic cities, each teeming with countless galaxies, equivalent to stars in a terrestrial city, all interconnected by filaments of gas and dark matter. Just as cities on Earth are hubs of activity, superclusters are centers of galactic life, places where galaxies interact, merge, and evolve in a complex cosmic dance. Our Milky Way galaxy is part of the local group, which itself is a member of the even larger Virgo supercluster. This supercluster contains thousands of galaxies, all bound together by gravity, forming a sprawling metropolis of cosmic proportions. Within superclusters, galaxies are not evenly distributed, but tend to cluster together in groups and clusters. These smaller structures are like neighborhoods within a city, each with its unique characteristics and population of galaxies. Some clusters are densely packed with galaxies, while others are more loosely bound, with galaxies spread out over vast distances. The study of superclusters provides valuable insights into the formation and evolution of galaxies and the large-scale structure of the universe. By mapping the distribution of galaxies within superclusters, astronomers can learn about the processes that shape the universe and how galaxies came to be arranged in the patterns we observe today. Superclusters are not static structures, but are constantly evolving, growing, and changing over time. As the universe expands, superclusters continue to accrete new galaxies, drawing them in from the surrounding voids. This ongoing process of growth and evolution shapes the structure of superclusters and influences the properties of the galaxies within them. And with that understanding, our cosmic journey takes us closer to home as we turn to our own galactic neighborhood, examining the local group and its humble position within the grand cosmic web. Shifting our focus from the grand cosmic cities, let's zoom in to our more immediate cosmic neighborhood, the local group. This is the cluster of galaxies that includes our very own Milky Way, along with other familiar celestial bodies like Andromeda and the Triangulum Galaxy, also known as Messier 33. The local group is a relatively small gathering, containing just over 80 galaxies, most of which are dwarf galaxies, much smaller and fainter than our Milky Way or Andromeda. Imagine the local group as a small town nestled within the sprawling metropolis of the Virgo supercluster. It is a gravitationally bound system, meaning that all the galaxies within it are held together by their mutual gravitational attraction. The Milky Way and Andromeda are the dominant members of the local group, exerting a strong gravitational influence on the smaller galaxies around them. These smaller galaxies orbit the Milky Way and Andromeda, much like satellites orbiting a planet. Our local group, while seemingly isolated, is far from alone. It is a part of the larger cosmic web. It resides on the outskirts of the Virgo supercluster, connected to it by filaments of dark matter and gas. These filaments act as cosmic highways, channeling galaxies and gas into the supercluster. The local group is gradually being drawn towards the center of the Virgo supercluster, pulled in by its immense gravitational force. This means that our cosmic address is not just the local group, but also the Virgo supercluster and the even larger cosmic web that surrounds us. Understanding our place in the cosmic web provides a broader perspective on our existence. We are not isolated observers, but are an integral part of a vast, interconnected cosmic structure. Our galaxy, our local group, and our supercluster are all pieces of a grand cosmic puzzle, each playing a role in the evolution and dynamics of the universe. Having situated ourselves within the cosmic web, let us journey into the depths of space. We'll explore the Hubble Deep Field, a window into the universe's distant past. Now, venturing further into the cosmos, we arrive at a truly awe-inspiring sight, the Hubble Deep Field. This image, captured by the Hubble Space Telescope, offers an unprecedented glimpse into the universe's distant past, revealing a tapestry of galaxies in various stages of formation, each contributing to the intricate details of the cosmic web. Imagine peering through a keyhole into another dimension, a dimension where time and space converge to showcase the universe's hidden wonders. That's precisely what the Hubble Deep Field offers. It represents a small patch of sky, no larger than a grain of sand held at arm's length, yet it contains thousands of galaxies, some of the most distant and faintest ever observed. These galaxies, scattered across the Hubble Deep Field, are not randomly distributed. They are arranged in patterns that reflect the underlying structure of the cosmic web. Filaments of galaxies stretch across the image, connecting denser regions and voids, illustrating the interconnectedness of the universe on a grand scale. As you gaze upon this image, let your eyes wander through the swirling arms of spiral galaxies, the glowing embers of star-forming regions, and the faint, reddish hues of galaxies receding into the depths of time. Each galaxy tells a story of cosmic evolution, of stars being born and dying, of black holes growing and merging, of the universe gradually building itself up over billions of years. The Hubble Deep Field is not just a pretty picture, it's a treasure trove of scientific data. By studying the galaxies in this image, astronomers can learn about the early universe, the formation of galaxies, and the distribution of matter in the cosmic web. It provides a crucial window into understanding how the universe evolved from a nearly uniform state to the complex structure we observe today. Having marveled at the Hubble Deep Field, our journey continues as we delve into the cosmic microwave background, an echo from the early universe. Transitioning from the distant galaxies of the Hubble Deep Field, we now turn our attention to an even earlier epoch in the universe's history, exploring the afterglow of creation itself, the cosmic microwave background. The cosmic microwave background, often abbreviated as CMB, is the faint afterglow of the Big Bang, the event that birthed our universe approximately 13.8 billion years ago. It represents the earliest light we can observe, emitted when the universe was only about 380,000 years old, a time when it had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. Before this time, the universe was a hot, dense plasma of charged particles, making it opaque to light. As the universe expanded and cooled, this plasma thinned out, allowing photons to travel freely through space for the first time. These photons, now stretched by the expansion of the universe, reach us today as microwave radiation, with a temperature of about 2.725 degrees above absolute zero. It is a uniform glow across the entire sky, but with tiny temperature fluctuations, or anisotropies, at the level of a few parts per million. These minuscule variations are incredibly significant. These subtle temperature differences in the cosmic microwave background hold crucial clues about the formation of the cosmic web. They represent the seeds of density fluctuations that existed in the early universe, regions that were slightly denser than others. Over billions of years, gravity amplified these initial density variations, pulling in more and more matter to form the large-scale structures we see today: galaxies, clusters, and the vast filaments of the cosmic web. By studying the patterns of these temperature fluctuations, scientists can learn about the composition of the early universe, the distribution of matter, and the processes that shape the cosmic web. The cosmic microwave background provides a snapshot of the universe in its infancy, offering invaluable insights into its origin, evolution, and ultimate fate. Having looked at the afterglow of the Big Bang, we'll now consider simulations of the cosmic web, which help scientists deepen our understanding of this vast structure. Shifting our gaze from observational data to computational models, let's explore how scientists use supercomputers to simulate the cosmic web. These simulations are crucial tools that help us understand the structure and evolution of the universe on the largest scales. The process begins with a set of initial conditions derived from the cosmic microwave background, the very afterglow we just discussed. Scientists input data about the density fluctuations, the amount of dark matter and dark energy, and the laws of physics into sophisticated computer programs. These programs then simulate the gravitational interactions of billions of particles over billions of years, essentially replaying the history of the universe from its earliest moments. Supercomputers, with their immense processing power, are essential for these simulations. They perform trillions of calculations every second to track the movement and interactions of particles, modeling how gravity causes matter to clump together, forming the cosmic web. These simulations can take weeks or even months to run, pushing the limits of current technology. The resulting models reveal the formation of galaxies, clusters, and the vast filaments that make up the cosmic web. By comparing these simulated structures to observations of the real universe, scientists can test their understanding of cosmology and refine their models. These simulations also allow researchers to explore different scenarios and test hypotheses about the nature of dark matter and dark energy, invisible components that play critical roles in the universe's evolution. These simulations not only provide visual representations of the cosmic web, but also allow scientists to study the properties of galaxies and clusters within the simulated universe. They can track how galaxies merge and evolve, how gas flows through the filaments, and how black holes influence their surroundings. This level of detail is impossible to achieve through observations alone, making simulations an indispensable tool for unraveling the secrets of the cosmos. Now that we've explored how simulations help us understand the cosmic web, let's consider the role of a mysterious force in further shaping the expanding universe: dark energy. Exploring dark energy and its role, we find a mysterious force comprises about 68% of the universe's total energy density, making it a dominant component in the cosmos. Unlike dark matter, which pulls things together through gravity, dark energy acts as a repulsive force, pushing everything apart, accelerating the expansion of the universe. Imagine the universe as a rising loaf of raisin bread. The dough represents space, and the raisins, galaxies. As the dough expands, all the raisins move farther apart. Dark energy is like an extra ingredient in the dough that makes it rise faster and faster over time. This accelerated expansion has profound effects on the growth and shape of the cosmic web. In the early universe, when matter was denser, gravity dominated, and the cosmic web grew as matter clumped together to form galaxies and clusters. However, as the universe expanded and became more dilute, the influence of dark energy grew stronger. Its repulsive force counteracts gravity, slowing down the formation of new structures in the cosmic web. The filaments of the cosmic web, once destined to become denser and more tightly packed with galaxies, are now being stretched apart by dark energy. The voids, already vast expanses of emptiness, are growing even larger. This ongoing expansion not only changes the appearance of the cosmic web, but also affects the future of the universe. Understanding dark energy is one of the biggest challenges in modern cosmology. Scientists are using various techniques, such as studying distant supernovae and measuring the distribution of galaxies, to probe its properties. By unraveling the nature of this mysterious force, we can gain deeper insights into the past, present, and future of the cosmic web and the universe as a whole. Having looked at the impact of dark energy, let's now shift our attention to some of the universe's most colossal formations, the largest structures known to exist. Turning our gaze towards the horizon of known space, we begin to explore the largest structures in the universe, colossal formations that dwarf even superclusters. These structures, like the Hercules Corona Borealis Great Wall, challenge our understanding of the cosmic web and its limits. The Hercules Corona Borealis Great Wall, one of the most immense structures discovered, stretches across an astounding 10 billion light-years. To put this into perspective, it would take light 10 billion years to travel from one end of this structure to the other. This massive collection of galaxies and galaxy clusters is so large that it occupies a significant portion of the observable universe. These structures fit into the cosmic web as the densest concentrations of matter within the network's filaments. They represent regions where gravity has had the most time and material to work with, pulling together countless galaxies into a single, vast entity. However, their sheer size raises questions about how they could have formed within the time frame allowed by the age of the universe, posing a puzzle for cosmologists. Studying these gigantic structures provides valuable insights into the distribution of matter and energy on the largest scales. They serve as testaments to the power of gravity and the ongoing processes that shape the universe. By observing their properties and mapping their locations, scientists can refine their models of cosmic evolution and gain a better understanding of the forces that govern the cosmos. These structures also highlight the interconnectedness of the cosmic web, illustrating how galaxies are not isolated islands, but rather components of a much larger, integrated network. The arrangement of galaxies within these structures reflects the underlying architecture of the cosmic web, with filaments acting as bridges, connecting different regions, and voids, defining the boundaries between them. Having explored these vast structures, we now turn our attention to the cosmic web and time, examining how the universe's grand design has evolved across billions of years. Now, as we shift our perspective, let's consider the cosmic web and time, exploring the eons over which this grand structure has evolved. From its infancy in the early universe to its present-day form, the cosmic web has undergone a remarkable transformation. In the immediate aftermath of the Big Bang, the universe was an extremely hot, dense plasma, nearly uniform in density. However, tiny quantum fluctuations seeded the structure we observe today. As the universe expanded and cooled, gravity began to amplify these initial density variations. Regions with slightly more matter attracted even more, gradually forming the seeds of galaxies and larger structures. Over billions of years, these subtle density enhancements grew into the vast network of filaments and voids that characterize the cosmic web. Dark matter played a crucial role, providing the gravitational scaffolding upon which ordinary matter could accumulate. Galaxies formed within the densest regions, clustering together to create groups, clusters, and superclusters. The passage of time on a cosmic scale is almost incomprehensible. Billions of years blur together as the universe continually expands and evolves. Galaxies merge, stars are born and die, and black holes grow in size. The cosmic web, too, continues to evolve, with filaments stretching and voids expanding as dark energy accelerates the expansion of the universe. Imagine watching a time-lapse video of the cosmic web's evolution, spanning billions of years. We would see the subtle dance of matter and energy, the gradual emergence of structure from chaos, and the ongoing interplay between gravity and expansion. It is a story of immense proportions, unfolding across vast stretches of space and time. Understanding the cosmic web's evolution requires sophisticated computer simulations that model the complex interactions of gravity, dark matter, and dark energy. These simulations allow scientists to trace the formation and evolution of cosmic structures, providing insights into the processes that have shaped the universe we observe today. With all this in mind, It is time to turn our attention to the intergalactic medium, the diffuse gas that permeates the space between galaxies, and its role within the cosmic web. The intergalactic medium, often abbreviated as IgM, is the rarefied, tenuous gas that dwells in the vast spaces between galaxies. It is the cosmic web's unseen scaffolding, an ethereal substance that connects and permeates the universe. This diffuse gas is not empty space. It is composed primarily of ionized hydrogen and helium, remnants from the Big Bang. The IgM is incredibly hot, with temperatures ranging from 10,000 to 10 million degrees Kelvin. This extreme heat keeps the gas ionized, preventing it from clumping together to form stars. The intergalactic medium plays a crucial role in the cosmic web, acting as a reservoir of matter that feeds galaxies and fuels star formation. As galaxies move through the cosmic web, they accrete gas from the IgM, replenishing their supply of star-forming material. This process helps galaxies sustain their activity and evolve over time. Imagine the cosmic web as a giant circulatory system, with galaxies as organs and the intergalactic medium as the lifeblood that flows between them. This lifeblood carries essential nutrients, enabling galaxies to thrive and grow. The IgM is not uniformly distributed. It is denser in the filaments of the cosmic web and more rarefied in the voids. These density variations reflect the underlying structure of the dark matter distribution, which shapes the cosmic web. Studying the intergalactic medium presents significant challenges due to its low density and faint emission. Astronomers use various techniques to probe the IgM, including absorption spectroscopy of distant quasars. As quasar light passes through the IgM, it is partially absorbed by the gas, creating a unique spectral signature that reveals its composition and properties. The intergalactic medium is a key component of the cosmic ecosystem, linking galaxies together and influencing their evolution. By studying this diffuse gas, we can gain insights into the formation and evolution of the cosmic web and the universe as a whole. As we continue our exploration of the cosmic web, let's now direct our attention to understanding how light travels through this vast structure, bending and stretching as it interacts with matter and gravity. Now, envision light embarking on its cosmic journey through the vast expanse of the cosmic web, a spectacle where the fundamental laws of physics orchestrate a mesmerizing dance. As photons traverse the universe, they encounter regions of varying density and gravity, causing their paths to bend and distort in ways that reveal the underlying structure of the cosmos. When light encounters a massive object, such as a galaxy or a cluster of galaxies, its path curves due to the warping of spacetime caused by gravity. This phenomenon, known as gravitational lensing, acts like a cosmic magnifying glass, bending and amplifying the light from distant objects. Gravitational lensing can create multiple images of the same object, or distort its shape into arcs and rings. These distortions provide astronomers with valuable information about the mass distribution of the lensing object, allowing them to map the distribution of dark matter in the cosmic web. Imagine a distant quasar, its light traveling billions of light years to reach us. As the light passes through the cosmic web, it encounters a massive galaxy cluster. The cluster's gravity bends the light, creating multiple images of the quasar, each slightly distorted and magnified. By analyzing these images, astronomers can determine the mass and distribution of dark matter within the galaxy cluster. The bending and stretching of light through the cosmic web are not merely an astronomical curiosity. They are a powerful tool for studying the structure and evolution of the universe. By observing how light is distorted, we can probe the distribution of matter, both visible and dark, and gain insights into the processes that have shaped the cosmos. As light journeys through the cosmic web, it paints a vivid picture of the universe's underlying architecture. Let's now turn our attention to understanding gravity's role in shaping the cosmic web, pulling matter together to form filaments and clusters. Transitioning into another key aspect of the cosmic web's formation, let's focus on gravity's profound influence. Gravity, that invisible force that binds us to Earth, also plays a pivotal role in shaping the large-scale structure of the universe. It is the architect of the cosmic web, orchestrating the dance of matter across vast cosmic distances. Gravity acts as the ultimate sculptor, drawing matter together to form the intricate structures we observe. From the earliest moments of the universe, gravity amplified tiny fluctuations in density, gradually pulling matter from less dense regions into denser ones. Over billions of years, this process led to the formation of the cosmic web's characteristic features: the vast filaments, dense clusters, and expansive voids. Imagine gravity as a cosmic spider, spinning an immense web of interconnected structures. The filaments of the cosmic web are like the threads of this web, composed of galaxies, gas, and dark matter, all drawn together by gravity's relentless pull. These filaments act as cosmic highways, guiding the flow of matter towards the densest regions of the universe. At the nodes where filaments intersect, gravity's influence is strongest, leading to the formation of massive galaxy clusters. These clusters are like bustling cosmic cities, home to hundreds or even thousands of galaxies, all bound together by their mutual gravitational attraction. Within these clusters, galaxies collide and merge, fueling the growth of supermassive black holes and driving the evolution of galaxies themselves. Even the voids, the seemingly empty regions of space between the filaments, owe their existence to gravity. As gravity pulls matter into denser regions, it leaves behind vast expanses of emptiness, creating the voids that characterize the cosmic web. These voids are not truly empty, however, they contain traces of gas and dark matter, remnants of the matter that once resided there. Gravity's influence extends far beyond the visible matter in the universe. Dark matter, that mysterious substance that makes up the majority of the universe's mass, also plays a crucial role in shaping the cosmic web. Dark matter interacts with ordinary matter through gravity, providing the scaffolding upon which the cosmic web is built. Without dark matter, the filaments and clusters of the cosmic web would not have formed as quickly or as efficiently, and the universe would look very different today. With a clearer understanding of gravity's role, we can now shift our focus to how the cosmic web influences star formation, with galaxies acting as cosmic nurseries where new stars are born. Now, Turning our attention to another fascinating aspect, let's explore how the cosmic web profoundly influences the birth of stars. Galaxies, nestled within the filaments and clusters of the cosmic web, serve as cosmic nurseries where new stars emerge, lighting up the universe with their radiant glow. The cosmic web acts as a vast network of cosmic fuel lines, channeling gas and matter towards galaxies. These filaments of gas provide the raw materials needed for star formation, acting as a constant supply of hydrogen and helium, the building blocks of stars. As gas flows along these filaments, it gradually accumulates within galaxies, increasing their density and triggering the collapse of molecular clouds, the stellar cradles where stars are born. Within these galactic nurseries, gravity takes over, compressing the gas and dust until it reaches a critical density. At this point, nuclear fusion ignites, and a new star is born, radiating light and energy into the cosmos. The cosmic web not only provides the raw materials for star formation, but also influences the rate at which stars are born. Galaxies located in dense regions of the cosmic web, such as galaxy clusters, tend to have higher rates of star formation compared to those located in more isolated environments. These densely packed galaxies experience frequent interactions and mergers, which can trigger bursts of star formation. As galaxies collide, their gas clouds compress and collide, leading to the rapid formation of new stars. This process can transform galaxies from relatively quiescent systems into starburst galaxies, ablaze with the light of millions of newly born stars. The cosmic web also plays a role in regulating star formation by controlling the flow of gas into galaxies. The filaments of the cosmic web act as a sort of cosmic thermostat, regulating the amount of gas that enters galaxies and preventing them from becoming too massive or too starved of fuel. This delicate balance ensures that galaxies continue to form stars steadily over billions of years, contributing to the ongoing evolution of the universe. The interplay between the cosmic web and star formation highlights the interconnectedness of the universe. The cosmic web provides the scaffolding upon which galaxies form and evolve, while galaxies, in turn, act as the cosmic furnaces where new stars are forged, enriching the universe with their light and energy. It's a beautiful dance between structure and creation, with the cosmic web orchestrating the birth of stars across vast cosmic distances. As we ponder the influence of the cosmic web on star formation, our journey continues into the enigmatic realm of black holes and their profound connection to the cosmic web. Transitioning our gaze now, let's turn to the enigmatic presence of black holes within the cosmic web. These cosmic behemoths, shrouded in mystery, play a crucial role in shaping the structure and evolution of the universe. Black holes, with their immense gravitational pull, act as anchors for galaxies within the cosmic web. Located at the centers of most galaxies, these supermassive black holes exert a powerful influence on their surroundings, dictating the movement and distribution of matter. As galaxies move through the cosmic web, they are drawn towards these gravitational anchors, like ships drawn to a harbor. The gravitational pull of black holes not only anchors galaxies, but also influences their movement within the cosmic web. Galaxies orbiting black holes experience tidal forces that can distort their shape and trigger bursts of star formation. These interactions can also lead to the merging of galaxies, resulting in the formation of larger, more massive systems. Furthermore, black holes play a crucial role in regulating the growth of galaxies. As matter falls into a black hole, it forms a superheated disk known as an accretion disk. This disk emits intense radiation, which can heat the surrounding gas and prevent it from collapsing to form new stars. This process, known as black hole feedback, helps to regulate the growth of galaxies and prevent them from becoming too massive. The relationship between black holes and the cosmic web is a complex and intertwined one. Black holes act as anchors for galaxies, influencing their movement and regulating their growth. In turn, the cosmic web provides the raw materials needed for black holes to grow and evolve. It's a symbiotic relationship that has shaped the universe as we know it. These mysterious objects, lurking within the hearts of galaxies, hold the keys to understanding the evolution of the cosmos. And now we can move to the next section. Now, let's shift our focus to another captivating question. Does the cosmic web hold the potential for life? While the vastness of space may seem empty, the intricate structure of the cosmic web raises intriguing possibilities about the distribution and development of life in the universe. Within the cosmic web, galaxies act as cosmic nurseries, providing the raw materials and conditions necessary for star formation. These stars, in turn, can host planets, some of which may be capable of supporting life. The cosmic web, therefore, serves as a framework for the distribution of potential habitats throughout the universe. The structure of the cosmic web may also influence the development of life in more subtle ways. For example, the filaments of the cosmic web can channel gas and dust towards galaxies, providing a steady supply of raw materials for star formation. This constant replenishment of resources may increase the likelihood of planets forming and sustaining life. Furthermore, the voids between the filaments of the cosmic web may offer unique environments for life to evolve. These voids are relatively empty and isolated, providing a refuge from the intense radiation and gravitational forces present in more crowded regions of the universe. Life in these voids may have evolved in unique and unexpected ways, adapted to the extreme conditions of their environment. Of course, the possibility of life existing within the cosmic web is still a matter of speculation. We have yet to discover any evidence of life beyond Earth, let alone within the cosmic web. However, the structure of the universe suggests that life may be more widespread than we currently believe. As we continue to explore the universe, we may one day discover evidence of life thriving within the cosmic web, forever changing our understanding of our place in the cosmos. With these thoughts in mind, let us consider Multiverse and its place in the vast cosmic scheme, which will be our next subject. Now, let us explore the multiverse and its possible connections to the cosmic web. The concept of the multiverse suggests that our universe may be just one of many, each with its own set of physical laws and constants. These universes could exist alongside our own, separated by vast distances, or even existing in different dimensions. If the multiverse exists, the cosmic web could be a structure that extends beyond our observable universe, potentially connecting different universes within the multiverse. Imagine the cosmic web as a vast, interconnected network, with each filament leading to a different universe. These universes could be vastly different from our own, with different laws of physics, different types of matter, and even different forms of life. The idea of interconnected universes raises profound questions about the nature of reality. Are these universes truly separate, or are they somehow connected at a deeper level? Does the cosmic web play a role in mediating interactions between universes? Of course, the existence of the multiverse is still a matter of speculation. We have no direct evidence of other universes, and it may be impossible to ever detect them directly. However, the theoretical framework of the multiverse provides a tantalizing glimpse into the vastness and complexity of reality. If the multiverse does exist, the cosmic web may be just one small part of an infinitely larger structure, a structure that encompasses all of reality. As we continue to explore the universe, we may one day discover evidence of the multiverse, forever changing our understanding of our place in the cosmos. With the concept of multiverse in mind, now let's consider how might it feel to journey through the cosmic web, venturing along filaments and through voids to uncover the riddles of the cosmos, which will be our next subject. Now, envision the prospect of human exploration within the cosmic web, traversing its filaments and voids to unveil the universe's enigmas. Picture spacecraft, not gliding through the familiar emptiness of our solar system, but navigating the faint, ethereal tendrils of the cosmic web. These filaments, immense rivers of galaxies and gas, stretch across billions of light years, forming a skeletal framework for the universe. Imagine explorers embarking on journeys along these cosmic highways, their vessels propelled by advanced propulsion systems, perhaps harnessing the very fabric of spacetime. They would witness breathtaking vistas, galaxies like luminous pearls strung along these filaments, each a unique island universe teeming with billions of stars. As they ventured into the voids, the immense, sparsely populated regions between the filaments, they would confront the profound silence and solitude of space. These voids, almost devoid of matter, offer a glimpse into the universe's earliest moments, preserving the faint echoes of the Big Bang. Here, shielded from the gravitational influences of galaxies, scientists could conduct experiments to test the fundamental laws of physics, probing the nature of dark energy and dark matter. The challenges would be immense, navigating the subtle gravitational forces of the cosmic web, avoiding the rare but potentially hazardous collisions with intergalactic gas clouds, and maintaining contact with Earth across vast cosmic distances would demand ingenuity and cutting-edge technology. Yet, the rewards would be immeasurable. Unraveling the secrets of the cosmic web would provide profound insights into the universe's origins, its evolution, and its ultimate fate. It could also reveal new forms of energy, new elements, and perhaps even evidence of life beyond Earth. As humans traverse the cosmic web, they would not only be explorers, but also ambassadors, carrying the hopes and dreams of humanity to the far reaches of the cosmos. Each discovery, each encounter, would enrich our understanding of our place in the universe and inspire future generations to reach for the stars. Now, let's consider how this grand structure has inspired artists and creators throughout history, which will be our next topic. Turning our gaze from the potential for cosmic voyages, let's now venture into the realm of artistic expression, where the cosmic web serves as an extraordinary muse for artists and creators. Through their interpretations, the grandeur and complexity of the universe find new dimensions, blending science with aesthetic emotion. Artists, inspired by the intricate patterns and vast scale of the cosmic web, translate the universe's hidden architecture into paintings, sculptures, and digital installations. These artworks capture the ethereal beauty of galactic filaments and the profound emptiness of cosmic voids, inviting viewers to contemplate their place within this grand design. The swirling structures of galaxies and the delicate balance of cosmic forces are reimagined through color, form, and texture, offering unique perspectives on the universe's underlying order. Consider the works of digital artists who simulate the cosmic web using algorithms and complex data sets. They craft immersive experiences that allow audiences to journey through virtual representations of the universe, witnessing the formation of galaxies and the dance of dark matter. These digital artworks not only showcase the beauty of the cosmic web, but also serve as educational tools, making complex scientific concepts accessible to a wider audience. Sculptors, too, find inspiration in the cosmic web, creating three-dimensional representations of its intricate structures. Using materials such as glass, metal, and light, they construct delicate frameworks that evoke the interconnectedness of the universe. These sculptures capture the essence of cosmic filaments, conveying a sense of both fragility and immense scale. The interplay of light and shadow within these artworks mirrors the dynamic processes that shape the cosmic web, from the gravitational pull of dark matter to the expansion of the universe. Moreover, the cosmic web inspires musical compositions, with composers translating the mathematical harmonies of the universe into sonic landscapes. By using data from astronomical observations, they create melodies and rhythms that reflect the patterns and processes of the cosmic web. These compositions invite listeners to immerse themselves in the symphony of the cosmos, experiencing the universe through sound. Through these diverse artistic expressions, the cosmic web becomes more than just a scientific concept. It evolves into a source of wonder and inspiration. The blend of science and art creates new avenues for understanding our universe, making both its beauty and its complexity palpable and accessible. Transitioning from the artistic realms inspired by the cosmic web, we now consider the philosophical implications that arise from contemplating our place within this vast structure. Transitioning from the artistic realms inspired by the cosmic web, we now consider the philosophical implications that arise from contemplating our place within this vast structure. The cosmic web and philosophy intertwine as we ponder profound questions about our existence and the universe's nature. Exploring the philosophical implications of the cosmic web invites us to reflect on our significance within the grand scheme of the cosmos. As we observe the vast network of galaxies, filaments, and voids, questions arise about our place in the universe, our purpose, and the very nature of reality. The sheer scale of the cosmic web challenges our anthropocentric views, urging us to consider that humanity is but a small part of something far greater. The cosmic web also raises questions about determinism and free will. If the structure of the universe is governed by physical laws and the gravitational interactions of matter, does this mean that our actions and choices are predetermined? Or is there room for agency within the cosmic framework? These questions have occupied philosophers for centuries, and the cosmic web offers a new context for exploring them. Contemplating the interconnectedness of the cosmic web leads us to consider the nature of existence itself. The universe appears to be a vast, interconnected network, with galaxies and clusters linked by filaments of dark matter and gas. This interconnectedness suggests that everything in the universe is related, and that our actions can have far-reaching consequences. The cosmic web, therefore, encourages us to embrace a holistic view of reality, recognizing the interdependence of all things. Moreover, the cosmic web prompts us to reflect on the limits of human knowledge. Despite our scientific advancements, much about the universe remains mysterious. Dark matter, dark energy, and the origins of the cosmic web itself are still subjects of intense research and debate. This recognition of our limitations can lead to intellectual humility, fostering a sense of wonder and curiosity about the unknown. As we ponder these philosophical questions, it is important to approach them with both reason and intuition. The cosmic web is not only a scientific phenomenon, but also a source of inspiration and awe. By combining scientific understanding with philosophical reflection, we can gain a deeper appreciation of our place in the universe and the nature of existence. Having pondered the philosophical implications, next let's imagine what it would be like to explore the cosmic web, traveling through filaments and voids to discover the secrets of the universe. Turning our gaze towards the horizon of time, we now consider the cosmic web and the future as the universe continues its eternal expansion and evolution. The destiny of this vast structure is intertwined with the fundamental forces that govern the cosmos, offering endless possibilities for change and transformation. As dark energy propels the universe outward at an accelerating rate, the cosmic web will continue to stretch and thin. The filaments that connect galaxies and clusters may become more elongated, and the voids between them will grow even larger. This expansion affects the formation of new structures as the density of matter decreases, making it harder for gravity to pull together new galaxies and clusters. Despite the overall thinning of the cosmic web, local regions with sufficient density may still experience the formation of new structures. Galaxies may merge, and new stars may be born within these cosmic nurseries. The interplay between gravity and expansion will shape the future distribution of matter, leading to a dynamic and ever-changing cosmic landscape. The future of the cosmic web is also linked to the evolution of dark matter and dark energy. As we continue to unravel the mysteries of these enigmatic components, our understanding of the universe's fate will deepen. Scientists are using advanced simulations and observations to model the long-term evolution of the cosmic web, exploring different scenarios and predicting the outcomes. In the distant future, as the universe expands further, the observable universe will shrink. Galaxies will recede beyond our cosmic horizon, becoming invisible to us. The cosmic web will become increasingly diffuse, with only the most massive structures remaining gravitationally bound. Yet, even in this distant epoch, the universe will continue to evolve, driven by the fundamental laws of physics. The possibilities that lie ahead inspire wonder and curiosity. The cosmic web, as a testament to the universe's grandeur, invites us to contemplate the endless cycles of creation and destruction. As we explore the depths of space and time, we gain a deeper appreciation of our place in the cosmos and the countless secrets that await discovery. Looking ahead, let's connect the cosmic web to the concept of dreams, using its vast, interconnected structure as a metaphor for the human mind. Venturing further into the realm of thought, the cosmic web invites us to consider the landscape of dreams, using its intricate and expansive structure as a metaphor for the human mind. Just as galaxies cluster and connect across vast distances through gravity, so too do our thoughts and memories intertwine within the boundless expanse of our consciousness. In the realm of dreams, the mind constructs a universe of its own, mirroring the complexities of the cosmic web. Each dream is a galaxy, a cluster of ideas, emotions, and experiences, drawn together by the gravitational pull of our deepest desires and fears. Like filaments connecting galaxies, associations and narratives weave through our subconscious, linking disparate elements into coherent, if often surreal, stories. The voids of the cosmic web find their counterpart in the blank spaces of our minds, the moments of quiet contemplation, where thoughts drift and new connections are formed. These mental voids are not empty, but rather full of potential, the fertile ground from which new insights and creative ideas can emerge. Exploring this metaphor, we find that the human mind, like the cosmic web, is constantly evolving. Thoughts come and go, memories fade and are reshaped, and new connections are forged, mirroring the dynamic processes that shape the universe. Dreams, in this context, are not just random firings of neurons, but rather glimpses into the vast, interconnected network of our inner cosmos. The sheer scale of the cosmic web, with its billions of galaxies spread across unimaginable distances, is reminiscent of the infinite possibilities of the human mind. Just as astronomers use telescopes to peer into the depths of space, we can use introspection and mindfulness to explore the depths of our own consciousness. As we drift off to sleep each night, we embark on a journey through our personal cosmic web, a universe of our own making. Understanding the cosmic web, therefore, provides a new lens through which to view our dreams, appreciating their complexity, their vastness, and their ability to reveal the hidden connections within our minds. Let's shift our focus now to how the cosmic web mirrors the journey into sleep, acting as a metaphor for the subconscious mind. Transitioning our thoughts, let us now consider the cosmic web as a grand metaphor for our nightly descent into sleep. As we prepare to rest, the boundaries of our conscious awareness begin to dissolve, much like the edges of galaxies fading into the vastness of intergalactic space. The familiar structures of our waking thoughts disperse, making way for the fluid, dreamlike landscapes of the subconscious mind. The vastness of the universe, with its countless stars and galaxies, mirrors the infinite depths of our subconscious. Just as the cosmic web connects disparate points in space, Sleep weaves together fragments of our daily experiences, emotions, and memories into a tapestry of dreams. The sheer scale of the cosmos echoes the boundless capacity of our minds to create and explore. As we drift deeper into sleep, the dense clusters of our conscious thoughts begin to thin out, resembling the filaments of the cosmic web stretching across the voids of space. These filaments represent the lingering threads of our waking concerns, gradually fading as we enter the deeper stages of slumber. The voids, those seemingly empty spaces between the filaments, become the fertile ground for the emergence of new, unexpected ideas and insights. In this state, our minds are free to wander, unconstrained by the limitations of logic and reason. Like photons traveling through the cosmic web, our thoughts bend and twist, following the contours of our subconscious landscape. We may encounter strange and surreal scenarios, bizarre juxtapositions of familiar and unfamiliar elements, all reflecting the unique architecture of our inner universe. The journey into sleep, therefore, is akin to embarking on a cosmic voyage. As we lose ourselves in the depths of our subconscious, we gain access to a realm of infinite possibilities, a universe of our own creation. This nightly exploration allows us to process our experiences, make sense of our emotions, and ultimately awaken refreshed and renewed, ready to face the challenges of a new day. With that in mind, we can reflect on our connection to the cosmic web and how it connects to you. Considering these connections, we turn to understanding your place within the cosmic web. You, as a conscious observer, are an integral part of this grand design. Every atom in your body was forged in the heart of a star, scattered across the cosmos by ancient supernovas, and eventually coalesce to form the matter that makes you who you are. This means you are quite literally star stuff, deeply connected to the universe on a fundamental level. Imagine yourself as a tiny but significant node in this vast network. Your thoughts, feelings, and actions ripple outwards, influencing the world around you in ways you may not even realize. Just as galaxies interact across cosmic distances, you are connected to others through networks of relationships, communities, and shared experiences. Each interaction, each connection, strengthens the threads of this human web, mirroring the intricate structure of the cosmic web itself. Moreover, your perspective, your unique viewpoint on the universe, is something precious and irreplaceable. No one else sees the cosmos quite as you do. Your existence contributes to the overall richness and diversity of the universe, adding a unique note to the cosmic symphony. Embrace this sense of belonging, knowing that you are not merely an observer, but an active participant in the ongoing evolution of the cosmos. Recognizing this deep connection can bring a sense of peace and purpose. It reminds us that we are not alone, adrift in an indifferent universe. Instead, we are part of something vast, beautiful, and interconnected. As you rest tonight, consider this bond, allowing it to soothe your mind and ease you into a restful sleep. Now let's come to the conclusion. In summary, the journey through the cosmic web has revealed a structure of immense beauty and profound mystery. From the smallest particles to the largest superclusters, the universe is interconnected in ways that continue to inspire awe and wonder. We began by exploring the origins of this vast network, tracing its development from the Big Bang to the present day. We uncovered the hidden influence of dark matter and dark energy, the enigmatic forces that shape the cosmic web. We witnessed how galaxies form along filaments of cosmic matter, lighting up the universe like beacons in the night. We contemplated the vast voids, the empty spaces that highlight the intricate structure of the web. We considered our place within this grand design, realizing that we are not just observers, but active participants in the ongoing cosmic drama. As you prepare to sleep, let these images and ideas gently fill your mind. Envision the cosmic web stretching out in all directions, connecting everything in the universe in a delicate dance of gravity and light. Feel the rhythm of the cosmos, the ebb and flow of matter and energy that has shaped the universe for billions of years. Now let your thoughts drift away like stardust, carried on the gentle currents of the cosmic web. Release any tension or worries you may be holding on to, knowing that you are part of something much larger than yourself. Allow the beauty and mystery of the universe to soothe your soul and ease you into a deep, restful sleep. May your dreams be filled with the wonders of the cosmos as you drift off to slumber under the watchful eyes of the stars. Good night, and may the universe watch over you. you.